Hi, my name is Michael Sullivan. I am a statistics and mathematics instructor at Joliet Junior College. I've been teaching at Joliet Junior College for over 20 years, and it is the oldest public community college in the country, chartered in 1901. Today, I would like to talk to you about threading a data set throughout your Introductory Statistics course. One of the skills we want our students to develop is to learn how to identify the type of analysis that might be conducted on any given data set. In addition, folks would love to have some form of capstone project that allows the student to see how the different statistical tools we provide to them may be used to analyze data. To assist in this regard, I have developed a series of problems built around a single data set. These problems are available both in the text and in the MyLab program. One aspect of MyLab that is awesome is its ability to randomly generate data based on a similar scenario. Unfortunately, because the data is randomly generated, the original story behind the data is lost, and we are left with country A or a reputable polling agency. To address this concern, I have written algorithms around this large data set that provides both the algorithmic nature of MyLab along with the authenticity of real data. As we progress through the various problems written around this data set, I will point out the corresponding MyLab problem available with statistics-informed decisions using data, which is now available in its 6th edition. Should you have any questions, feel free to email me at sullystats@gmail.com. The problems in the text are based on all tornadoes that struck the U.S. in 2017 and is available in StatCrunch. So here's the data in StatCrunch, and you can see there are a wide variety of variables measured, including the state, the F-scale, which is a measure of wind speed, injuries, fatalities, property loss, length of the tornado in miles, width of the tornado in yards, number of states that the tornado struck, and then a last variable called F0, which is whether or not the tornado was an F0 tornado. The data come from the National Oceanic and Atmospheric Administration. Notice that you could adapt the problems to address all tornadoes that struck the U.S. since 1950. So now I'm going to go through all the different problems that have been written based on this data set. I'm going to go in sequential order of the text. So in this particular problem, all the student is required to do is draw a relative frequency bar graph of F-scale, recognizing that F-scale is a qualitative variable. I want to point out in part D, we're asking the student to create a graphical summary that will display which month had the most tornadoes. We are not telling them the type of graph that needs to be drawn. This problem is also available in the MyLab as 2.1.25-T. Here, we're organizing quantitative data. Notice in part D, we are bringing the qualitative variable state into the mix by only drawing a histogram of tornado length for tornadoes that struck the state of Texas. You could choose any state you wish. Here we're looking at measures of central tendency. Look at part C. Property loss is a highly skewed to the right variable. Students are asked to compute the mean and median along with a graph, again not specified, that will confirm the skewness of the distribution of the variable property loss. Look at part D. Does it make sense to determine the mean F-scale? F-scale, of course, is a qualitative variable, but it's a numeric quantity. Students need to recognize that qualitative variables periodically show up as numerical quantities, and therefore the mean would not make sense for the variable F-scale. Graphical and numerical analysis is used to consider the spread of the variable length. Here, we're using the interquartile range to judge dispersion. Again, notice that we are doing this by state. We are only selecting the state of Iowa and comparing it to the interquartile range of the length of tornadoes in Kansas. Now what we're going to do is look at box plots. We compare the length by month using side-by-side box plots. We also narrow the data set down, comparing F2 scale tornadoes to F3 scale tornadoes. Note that we're giving the direction on how to get this data using StatCrunch. This problem considers everything you would want to do to summarize bivariate quantitative data in the Introductory Statistics course. The question is a tornado's width related to its length? This particular problem only looks at tornadoes from the state of Louisiana. However, this problem could easily be adapted to consider any other state as well. This particular problem is a simple probability model for F-scale. Now what I want to do is show you how this data set can also be used to develop statistical concepts like the central limit theorem. We're going to use the sampling distribution applet with this tornado data. So the tornado data for 2017 is loaded into the StatCrunch spreadsheet. I'm going to select Applets, Sampling Distributions. What we can do here is grab the data from the data table. I'm going to consider the variable length. We can title the applet as well. So this is length of all tornadoes in 2017. Hit compute. Now what happens in the applet is the population data length of all tornadoes appears in the top window. Notice that the distribution of the variable length is highly skewed to the right. The applet tells you the population mean as well as the population standard deviation. In this second window, we can choose a sample size. Let's say I choose a sample size of 9. When I click one time, the applet randomly grabs 9 tornadoes from the population data, records the length of those tornadoes, and then in the bottom cell reports the sample mean. So the sample mean of that one sample is 2.89 miles. I'll do this one more time. Click one time. The applet randomly selects 9 tornadoes from the population data, records its length in the middle cell, and in the bottom cell reports the mean of those 9 observations. Of course, we can do this many times. So you can click 1,000 times, say 5 times, to get a total of 5,002 samples from this population. The 3.773 is the mean of all those sample means. Point out to the student that that equals the population mean. The standard deviation of all those sample means is 2.01, which is less than the standard deviation of the population data. In addition to that, the student can click these 3 bars and zoom the x-axis to see that the distribution of those 5,002 sample means is still skewed to the right. Hit reset and play around with this for different sample sizes. So let's say we want to do a sample of size 40. I click 1,000 5 times to get 5,000 sample means. The mean of those 5,000 sample means is close to the mean of the parent population. The standard deviation is 0.94, which is less than the standard deviation of the population. The distribution of those sample means is still skewed to the right, but less skewed than it was when n was 9. At this point, students are starting to figure out that as the sample size n goes up, the standard deviation of x bar goes down, and you can continue playing with this for different sample sizes to show that as the sample size n increases, the distribution of x bar eventually becomes approximately normal. For this particular variable, the length of the tornadoes is so skewed to the right that it requires a rather large sample size before we can invoke the central limit theorem. But at this point, again, the students understand that the mean of x bar is equal to the mean of the parent population regardless of sample size, and that the standard deviation of x bar is sigma over the square root of n, and that formula works as well regardless of sample size. And then finally, the central limit theorem has to do with the shape of the distribution of x bar as the sample size n increases. I completely recommend that you do this with other distributions as well, so that students can get a sense for the nature of how large n has to be before we can invoke the central limit theorem. So like here, I hand drew a histogram that is skewed to the right, and now when I hit 1,000 times a few times and zoom in on the x-axis for a sample size of 30, the distribution of x bar is approximately normal. And so again, it's the skewness in the distribution of the parent population that plays a role in how large the sample size needs to be before we can invoke the central limit theorem. Now let's use the confidence interval applet to illustrate the meaning of level of confidence, which is a tough concept for most of our students to understand. This last column over here on the right is whether or not a particular tornado is an F0 or not. And so you can see that in row 8, where the F scale is 0, we have a yes, and in any row where the F scale is not 0, we have a no. And so this is essentially a qualitative variable with two possible outcomes. Either the tornado has the characteristic that it's an F0 or it does not. To see how we can illustrate the meaning of level of confidence with this data, we go to Applets, Confidence Intervals for a Proportion. Again, I'm going to grab the data from the data table, and I'm going to grab the variable F0. You tell the applet that a success is a yes. We're going to construct 95% confidence intervals, and let's make the sample size, say, 80. A sample size of 80 is large enough to say that the distribution of p hat is approximately normal. I won't title the graph in this particular illustration. What the applet does now for you is it constructs 100 confidence intervals based on 100 different random samples of size 80 from this population data. You can construct as many intervals as you like to illustrate the concept of level of confidence. So for example here, 95 of the 100 intervals had a confidence interval that captured the population proportion. And by the way, we know the population proportion because we can just simply compute the proportion of F0 tornadoes in our data set by going to stat tables frequency of F0, and there you can see the proportion of F0 tornadoes is 0.432, and so that's what we see up here at the top of the applet. Now what you want to point out to your students is that these red confidence intervals are intervals where the population proportion is not included in the confidence interval. And for any of these intervals, you can highlight the red interval and see the raw data as well as the statistics corresponding to that particular random sample. So interval number 92, which is illustrated right here, is an interval that does not include the population proportion. Why does that happen? Because we only randomly sampled 17 out of 80 tornadoes that were F0 tornadoes. That is much less than the population proportion, and that's why my interval missed. So this particular random sample ended up with a sample proportion way in the left tail of the sampling distribution of p hat, whereas the intervals in the right like say interval number 28. Here we randomly sampled 45 out of 80 tornadoes that were F0. This is substantially higher than the population proportion, and so this sample proportion is in the right tail of the sampling distribution of p hat, and that's why the interval misses. How often will you end up with a sample proportion that's about 2 standard errors from the population proportion? About 5% of the time. It's those samples that result in confidence intervals that do not include the population proportion. And so this is a great way to illustrate the meaning of level of confidence using population data. Here's a problem that also has the student construct confidence intervals for a proportion. In one of the samples in part B, the interval includes the population proportion, while the data in part H is an interval that does not include the population proportion. Again, it allows the student to help understand the meaning of level of confidence. This is a similar problem based on a confidence interval for a mean. Here's a question you might ask. Is there a higher proportion of F0 tornadoes in Texas or Georgia than nationally? We know the population proportion of F0 tornadoes is 0.465. Again, you can do this for any state that you want. Or, are the lengths of tornadoes in Texas or any other state different than nationally? Again, we can determine the population mean length of all tornadoes because we have population data. Is there a difference in the proportion of F0 tornadoes between any two states, like say Texas and Georgia? Is there a difference in length of tornadoes between any two states? Or is there a difference in the length of F0 tornadoes versus F1 tornadoes? All you have to do is take a simple random sample of each. So the goal with this data set is to allow students to see how the various tools we are giving them can be applied to a single data set and learn to answer a lot of questions. Combined, all these problems could be the basis for a capstone project within the course. Should you have any questions, please don't hesitate to reach out to me at sullystats@gmail.com.